Hi everyone, my name is Agnieszka Slowik. I'm a research intern at Facebook AI, and I'm going to present linear unit tests for invariance discovery. If we intend to use an algorithm on new data outside of the training environment, we should consider any correlation that only holds in a training environment to be spurious. A spurious correlation is a correlation that only appears to be true due to a selection effect, such as selecting a training set. To be confident in our predictions in novel use cases, we want to learn a model that ignores spurious correlations and instead relies on features that affect the target in all environments. Spurious correlations obscure the real causal mechanism. For example, in image classification, exploiting background features often leads to ignoring the causal relations between the object features and the target. Several algorithms propose to learn invariance discovery by consuming several training datasets that represent the same problem. I'm going to refer to those as environments. If the interventions producing these environments are sufficiently diverse, invariances across the environments should correspond to the real causal mechanism. We investigated the current state of this multi-environment approach to invariance discovery, and we developed a benchmark for evaluating and comparing algorithms that learn invariant correlations across multiple environments. Interestingly, none of the invariance discovery algorithms mentioned here work well on the proposed suite of linear tasks. In all of the datasets in our benchmark, the feature vectors contain both the environment-specific spurious correlation and the signal that is invariant across all of the training distributions presented to the model. In the test split, we shuffle the spurious features across examples. This way, only those predictors ignoring spurious features will achieve a low test error. The first problem, linear regression, where features contain causes and effects of the target variable. By virtue of considering only valid interventions, the mapping from the causes to the target variable is invariant across environments. Conversely, the mapping from the target variable to the effects changes across environments. Next, we use a linear version of the cows versus camels problem. As the dimension of the feature space grows, it is becoming harder and harder for algorithms to resist the spurious dimensions. Invariance penalties based on a standard training error, such as IRM, may accept solutions using spurious features. Finally, we studied a problem where the first two dimensions offer an invariant small margin linear decision boundary. The rest of the dimensions offer a spurious large margin linear decision boundary. It is a linear version of the spiral binary classification problem proposed by Parascandolo. For each of these problems, additionally, we created scrambled variants by transforming the features using a random rotation matrix fixed for all of the environments. Observing a scrambled version of the variables appearing in the structural equation models requires algorithms to learn a linear feature representation under which the desired invariance should be elicited. We provide baseline results where we compare the algorithms mentioned previously to an oracle, a version of ERM which ignores spurious correlations. It is the purple bar in the plot, which corresponds to the upper bound performance. We observed that none of the existing algorithms solve these problems. IRM performs close to oracle only on example 1. In the paper, we also discussed the influence of varying the number of environments and varying the number of spurious features. As you might expect, increasing the number of spurious features lowers the performance further. Our benchmark is already available on GitHub. Thank you for your attention.